Hello guys, welcome back. We will be looking at factors affecting enzymes. So let's begin. Okay, so here we've got the specification, well, part of it, looking at enzymes, and here are the factors. So we're going to look at enzyme concentration, substrate concentration, competitive and non-competitive inhibitors, pH and temperature. So there are two ways rate of reaction is measured. But firstly, what is rate of reaction? Now, rate of reaction is basically the amount of product amount of product made over time, or sometimes, so just leave it as that. So how is a rate of reaction measured? So how fast a product is made, which is essentially this, and how fast a substrate is broken down, so the reactant. So let's take, for example, A plus B makes A B, so how fast these two are broken down or like reduced in concentration, and how fast AB is made, which is a product. So here we're looking at temperature as the first factor which affects enzyme rate of reaction. So more heat means more kinetic energy. Now, kinetic energy is basically movement, energy movement. So molecules move faster, and so the substrate molecules increase in collision with the active site of the enzyme, obviously. So binding them to make lots of enzyme substrate complexes. So basically, more heat means more kinetic energy. So then, as a result, because they have more kinetic energy, they're going to obviously move a lot faster, and so then it increases the chance of a collision. So the more you move about, the higher the chance of you colliding with something, obviously, and that thing it's going to collide with will be the active site of the enzyme. And then, because once it binds to the active site, obviously it makes an enzyme substrate complex, so we get an increase of these enzyme substrate complexes. However, increasing the temperature may result in bond breaking of the enzyme tertiary structure. So imagine here is two amino acids which have bonded together. So this is the bond, and these two are the amino acids. So what's happened is you're going to give a lot of heat energy, which allows a lot of movement. That movement, so much of it, can actually break the bonds, and as a result alter the structure. And because the tertiary structure is specific with certain bonds in certain places and amino acids in certain places, it can ruin and disturb the structure, the shape of the active site. So, like I've said here, and this whole disturbance is called denaturation, or the enzyme or the active site. The enzyme is now denatured, and then as a result, because the active site is no longer in shape or complementary to the substrate, then you can no longer make any enzyme substrate complexes. Now, in human body we have enzymes, obviously, and these enzymes work at an optimum temperature of 37 degrees. If it goes beyond the optimum temperature, then it can denature, and when it denatures, that basically means the bonds are broken, like I said before, and the active site is no longer complementary, therefore can't make any enzyme substrate complexes. Now, looking at pH, all enzymes have an optimum pH value. By the way, you've got to recognize the graphs for each one. So for temperature, this is what the graph looks like here. So I try and memorize that. So let's go back to pH. So all enzymes have an optimum pH value. Most humans enzymes work best at pH 7, but there are exceptions, such as like pepsin, so in the stomach, where it's all acidic conditions, so the enzymes there work best at pH 2. And the pH is simply a measure of hydrogen ion concentration. If you don't know what that means, basically it literally means the number of hydrogen ions you find in that environment, and that's basically what pH is, a measurement of the concentration of the number of hydrogen ions. Now the higher the concentration, the more acidic the pH will be. So in other words, the lower the pH will be. Sorry, that's phrasing correctly. So the more the hydrogen ions you have, the more acidic it is, the lower the pH. So altering the pH will alter the hydrogen ion or the hydroxide ion concentration, which can disrupt the ionic bonds and hydrogen bonds that hold enzyme tertiary structures in place. The main effect is to alter the changes on the amino acids that make up the tertiary structure. Any changes in pH will result in the denaturation of enzymes, therefore less enzyme substrate complexes. So you've got to look at this. A slight fluctuation to the left or to the right can involve denaturation of the enzyme, hence no less enzyme substrate complexes. Now this is also on the spec as well. Students could be given the hydrogen ion concentration of a solution in order to calculate its pH using the formula pH equals minus log 10. So I'd memorize this formula because it doesn't say you'll be given it, but just in case you won't be, then it's a good idea to memorize it. So literally you're plugging in this into your calculator. That's it. That's how you work out pH, and you just plug in your number and plug in this symbol here. So I think it's this that you're pressing, and then you get, so first you have to press this, then you press this, and then you insert your number. So work out the pH of this acid, which contains 2 times 10 to the power minus 2 hydrogen ions. So let's work it out. So first step is to press the minus symbol here. So we're going to press minus. Second step, we're going to press this button here. So it'll get minus log, and then we've got a box down here. In that box, we're going to put minus log 10. We literally type in 10, 1, 0. And then we've got this extra box here where we insert this number, this number right here. So 2 times 10 minus 2. And then we press equals, and then we should get something like, no idea. Can't do that in my head. No one can do that in their head. So you should get 1.7 or 1.69. Now, I think that's the same. Yep, that's the same. Okay, so now we can also work out the reverse. So we can work out the hydrogen ions from the pH, and this is the equation we use. So to work it out, we do 1 times 10 minus pH, whatever the pH is, and that's literally it, and that gives us the hydrogen ion concentration. So let's use the example we had before. So we had 1.69, or was it 1.7 as the pH. We want to work out the hydrogen ion concentration, so on your calculator I would put 1 times 10 minus either 1.69 or 1.7, and you should get 2 times 10 to the power minus 2. Okay, so now let's look at substrate concentration, another factor which affects enzyme rate of reaction. So the higher the substrate concentration, the faster the reaction. Now, more substrate molecules mean more likely. This keyword here, more likely, is really important. You'll see it on a lot of mark schemes. So more substrate molecules mean more likely collisions between substrate and enzymes, and so the active site will be more occupied. But there will be a certain point at which the addition of a substrate molecule will make no difference. Like you can see right here, it's making no difference. to the rate of reaction because each of the enzyme active site is occupied, so it's at a constant rate because all of the active sites are occupied. And the way we can defeat this settling point, this plateau, is to increase the number of enzyme concentration. Now, enzyme concentration, so this is another factor. More enzymes there are, the higher the chance there is for the substrate to collide with the active site, creating more enzyme substrate complexes. But there will be a point where adding more enzymes will not affect the rate of reaction, as there won't be enough substrate to occupy all active sites. So usually if there is enough substrate, it should look like this, and if there isn't, it should look something like this, because the substrate is no longer there, and therefore the enzyme's rate of reaction will slowly decrease because of the lack of substrate. Now, inhibitors, we've got two types. We've got competitive inhibitors, so these are substances which slow down the rate of enzyme controlled reactions, and it's in the name, it's competitive, so it will compete with other substrate molecules that are similar in shape to the substrate and bind to the active site exactly like a substrate, but just slightly change in shape, and they just compete with the other substrate. So imagine this competitive inhibitor is like your long lost cousin from Asia who's really good at his or her studies and really competes for the active site. Yeah, weird analogy, but anyways, hopefully you get the idea. And so they compete for the active site with the substrate, and they slow down the rate of reaction by preventing enzyme substrate complexes to be formed. Now you've got this other inhibitor called non-competitive inhibitors. It's in the name. It won't really need any competition because it's that good, because what happens is this non-competitive inhibitor doesn't bind to the active site, it binds to this other site away from the active site called the allosteric site. And once it binds, what happens is it changes the shape of the active site and therefore prevents any further enzyme substrate complexes to be made. So no matter how much substrate you add, having this non-competitive inhibitor will prevent any of the substrate to bind to the active site, even though it's unoccupied. So imagine it's like an on and off button. Once the non-competitive inhibitor binds, it's switching off the enzyme completely and therefore doesn't allow the substrate to bind. Now appreciate that enzymes catalyze a wide range of intracellular and extracellular reactions. So intracellular enzymes are synthesized and retained in the cell. So intra sounds like inside, and cellular basically means cell. And so enzymes are synthesized and retained in the cell for the use of cell itself, and they are found in the cytoplasm, nucleus, mitochondria, and chloroplast. For example, we have DNA helicase within the nucleus. Now, extracellular enzymes are synthesized in the cell but secreted from the cell to work externally. So, for example, digestive enzymes secreted in the pancreas but are transported to the duodenum. So that's it for today. Hopefully that's helped. If not, comment down below. If it has, comment down below. And if you want me to go over this video again, make anything better, please do, because I will. And next video we'll look at DNA.